All right, well, good afternoon, everybody. Good to see you. Welcome. Welcome to all those students watching on video as well. Before we start, we were talking about joinable and detached threads, and you asked the question about why you would ever want to have threads running in non-detached mode, why you'd ever want to have them running joinable. And I didn't give you a very good answer, so I want to try to answer that for you better. Turns out there's an important class of sort of parallel programming. There's an important parallel programming model called fork and join, where program consists of a series of phases. And in each phase you have a worker, or a master, sorry, and it creates a bunch of worker threads. And then each of those worker threads solves some part of the problem for that phase. Like, so maybe you take your data structure and you break it up into chunks, and then each thread updates its own chunk of that data structure. But for whatever reason, the master then has to wait for the worker threads to finish before it can go on to the next phase. So it does a join. So this is called the fork. And then it waits for all the threads to finish by doing a join. Okay, so this is called the fork, and this is called the join. And only when all of the threads have finished can it go and do the next phase. Okay, so this model is really important in things like scientific computing, where you might you're simulating some domain. You're simulating nature, so you represent that as some domain. Like maybe you're simulating how heat flows over a plate, a metal plate. And so you might have these workers. You might partition the domain amongst a set of those workers, and then each one of these phases is a time step. And then so once all the workers have finished a time step, then they can advance to the next time step. And so sorry, I don't know why I didn't think of that, but that's an important reason why you'd want this. Okay, so we've seen that threaded programs are nice because you can share all the global variables, but this sharing can have unintended consequences. So somehow we need a mechanism where we can control how the flows of each individual thread are interleaved, so that bad things don't happen when we share data structures. Okay, and so this process of controlling the interleaving is called synchronization. So we're going to look at techniques that you can use to write correct threaded programs by properly synchronizing them. Now first, though, we need to have a clear idea. So sharing is the issue, right? If we have threads that aren't sharing any resources, then there's no problem, right? That we saw this when we looked at processes. There's no shared data structures with processes. So processes just run independently. We don't really care how they're interleaved. No worries. Okay. But as soon as we introduce sharing, then we have to be careful. Okay. So to understand how to synchronize threads, we first need to have a clear idea of what we mean by sharing in threaded C programs. So the answer is not as simple as global variables are shared and stacked variables are not shared. Okay. Instead, a variable x is shared if and only if multiple threads reference some instance of that variable x. Right, so if only one thread is accessing a particular variable, then it's not shared. Okay, so in order to know exactly what we mean by shared, we need to answer three questions. Okay, first, what is the memory model for threads? Okay, second, how are instances of variables mapped to memory? And then third, how many threads might be referencing the instances of those variables? Okay, so we'll look at each of those now in turn, each of those three questions. Okay, so first is the memory model. The conceptual model is a little bit different from the operational model, the way it really works. Okay, so conceptually, we have multiple threads that run in the context of a single process. Okay, and some of that context is shared and some of it's not shared. So each thread has its own separate thread ID, stack pointer, program counter, condition codes, general purpose registers. And then they all share the remaining process context, which is data structures that the kernel maintains for the threads, the virtual data structures to support the virtual memory system, open files, install signal handlers, and so forth. So that's the conceptual model, and if that were really enforced, it would be nice. It would make things simpler for us. But unfortunately, in real life, this model is not strictly enforced. Now, although register values are really separate, right? The kernel maintains separate context for all the registers, so that part is good. But since the threads share the address space, a thread can access the memory, the stack. One thread can access the stack of another thread. Okay, so although conceptually these stacks are separate and distinct and private, they're really not. And so this can create some problems. So here's an example of that we'll come back to later of how this one thread can access the stack of another thread. So here we're defining a global variable called pointer, which is a char star star. And then in the main routine, we're declaring a local variable called messages, which contains, it's a two-element array which contains a couple strings, these will be printed out by the threads that we're going to create. And then we assign the global pointer to the address of the array messages. Okay, so now pointer points to messages. And then we create, in a loop, we create two threads, each of which executes this routine called thread, and we're passing an argument. So the pthreads will assign a thread ID, but in this case, we're going to assign our own local thread ID by passing this loop index. Okay, so this is an example. We talked about this last time. This is perfectly okay. There's no race. But it's a little weird because we're going to take this index I and cast it to a generic pointer. Okay. And then after we create these threads, then we'll exit the main thread. Now, the thread routine dereferences its argument to get the local thread ID, and then it declares a static variable count that we're going to use to count how many times this thread routine is called inside of a thread. And then it just prints a simple message from identifying giving the local thread ID, and then the message indexed by my ID. So pointer points to messages. So thread 0 will print hello from foo, and thread 1 will print hello from bar. And then we pre-increment the counter variable. Okay, so although it doesn't, it looks like we're accessing this global variable pointer, but since that was assigned to be the address of the local variable on the main thread stack, we've got these peer threads accessing local variables on the main thread stack. Okay, so this is not, you'd never want to do this. It's a very bad practice, but it's the kind of thing that can happen sometimes by accident. You know, if you forget that pointer actually was assigned to, some stack address. Okay, so the second question then is, how do we map variable instances to memory? Now we looked at this when we studied linking, but let's just review this quickly again to make sure that it's clear to you. So global variables are variables that are referenced outside of a function. And virtual memory, the linker, when it does symbol resolution, makes sure that there's exactly one instance of every global variable in virtual memory. Now, local variables are declared on the stack inside of a function without the static attribute. And so in this case, the stack for each thread will contain one instance of that local variable. Now, if variables are declared inside of a function with the static attribute, then the scope of that variable is limited to that function, meaning no other function can access it. But that static variable is stored along with all the other local variables. So there's any static variable declared inside of a function has exactly one instance in memory. And if you were to have, say, multiple functions that declared a static variable with the same name, the compiler would disambiguate those somehow. It would append some kind of unique, it would somehow make that name unique. Okay, so recall how all these different types of variable instances are mapped into memory. Okay, pointer is a global variable, so there's one instance of pointer in the address space. And it's stored in the data segment. I and messages are examples of local variables to main. So there's one instance of these stored on the stack of main stack. And we'll denote those with this notation. We'll say variable I.m means variable I is stored on main stack. And messages is stored on the stack of main. Okay, now my ID is a local variable defined in this thread routine. And so there's actually, since there's two of these threads, in memory there's two instances of my ID, one for each stack. Okay, associated with the stack associated with each thread. So my ID.P0 is stored on peer thread 0 stack, and my ID.P1 is stored on peer thread 1 stack. Okay. And now this counter variable, the static counter variable, has just exactly one instance in virtual memory, and it's in the data segment along with other global variables like pointer. Okay, now so the question is, which of these variables are shared and which are not? Okay. And so we can remember what we said is it's shared if more than one thread is accessing an instance of that variable. Okay. So let's just list all the different variables, and then let's look at each of these threads and see if it's referenced by that thread. Okay, so what about pointer? Right, it's referenced by the main thread, right? And what about peer thread 0? Yeah, it's referenced by peer thread 0 right here. Right here. And similarly for p thread 1. Okay, so pointer is referenced by all three threads. Now what about count? Count's not referenced by the main thread, but it is referenced by the two peer threads. Now what about I in main? That's referenced by main, of course, but not by either of the two threads. Now what about messages, the messages array? Okay, so that's accessed by main, and indirectly through pointer, it's referenced by each of these two peer threads. Now what about my ID defined in peer thread 0? Okay, so that's referenced, that's a local variable, so it's only referenced by peer thread 0, right? It's not referenced by either of the other threads. And similarly for my ID in peer thread 1. Okay, so given that definition then, which of these variables is shared? So it's really straightforward. Yeah?
Does count actually count as a shared variable because it's static? So wouldn't it be separate for both?
Okay, so the question is, does count as a shared variable? And the answer is yes, because it's declared static, there's one instance of it in virtual memory, and each of the threads references that instance. Okay, so it's shared. It's really like a global variable. It's just the scope is limited to it's stored the same way a global variable is, but its scope is limited to the function that it's defined in. Okay, so to determine if each one of these is which of these variables is shared and which one's not, we just go across, and for any variable that's shared by more than one thread, then it's shared. So pointer is shared. So pointer is shared. Count is not shared. Count is shared because it's referenced by peer thread 0 and peer thread 1. I is not shared because it's only referenced by main. So messages is referenced by all three threads, so it's shared. But my ID is not shared because it's only referenced by exactly one thread. Okay, so pointer, count, and messages are the shared variables in this program, and the others are unshared. Yes?
So if you declared my ID as static, would like the second process have overwritten process 1?
So if you declared my ID as static, would the second process have overwritten it? Yeah, that would be a race. Okay, so it would just depend on which thread executed first. So you really wouldn't want to do that. Okay, so we have a very clear notion now of what we mean by sharing. So being able to share variables like this in this way is very handy, but you can run into some really nasty problems that are very surprising. So let me show you an example. This is a program called bad count, so obviously there's something wrong with this. I'm giving you a little clue. But what we want to do is we want to create a bunch of threads, or a number of threads, and each of those threads will increment a global variable called count some number of times, the same number of times. Okay. So we pass in the number of iterations as the first argument. And here's our globally shared variable. And do you remember what volatile means? Everybody remember what that means? So what does volatile tell the compiler? Yes?
It tells the compiler that value might be modified outside the scope of what we're doing here. And so we can't trust that value is going to be the same between accesses. It
actually, you're in the right direction. It actually tells the compiler never to put that variable in a register. Okay, so it will always read that value from memory or store it to memory, and you do that because of exactly the kind of possibility that you mentioned. So So in this case, we have we create two threads with two distinct calls to pthread create. Each of these threads will run the thread routine called thread, and it will pass as an argument the address of the number of iterations that it should iterate. Now you remember when we were passing connected file descriptors, if we passed an address, that was a race. Okay, but in this case, there's no race. This is fine. It's fine just to pass the address of number of iterations. So why is it okay in this case, but it wasn't okay when we were passing the connected file descriptor that we got from accept into our thread routine? Yes?
The thread doesn't modify the value?
Exactly, because the thread doesn't modify the value. And the problem we had before was that our main thread was modifying that connected descriptor on the next call to accept. But here it's just a read-only variable, so we're okay. But you see how tricky the reasoning can get, right? You can't do pattern matching to determine whether you've got races or not races. Right? So you can't just say, well, it's always bad to pass the address of some variable to a thread routine. Okay, because it's not. It just depends on the context. Okay, so in this case, we're passing the number of iterations to each thread. And then we're waiting for each of those threads to finish. So this is another example of why you need, why you might want to have a non-detached thread, because you can't. When we check the value of count, we have to make sure that every thread is finished before we check whether we got the right value or not. Okay, so we wait for each thread to finish. And now, since we've created two threads, each of which is incrementing count n iters time, we expect count to be equal to 2 times n iters. And if it's not, we print my favorite error message. Otherwise, with the value of count. Otherwise, we print OK, also with the value of count. Okay, so now what's going on in the thread routine? Very simple. It dereferences the argument that was passed in and stores it in the local copy of n iters. And then it loops n iters time and increments count each time. So, and then returns. So this is very innocuous. What could go wrong? Right? And since this is threading, since this is concurrent programming, and especially since it's threaded programming, lots of subtle things can go wrong. So it turns out this program has a really serious bug. Okay, because when we run it on a Linux box, sometimes, if we call it with an argument of 10,000, sometimes we get the correct answer, 2 times 10,000 or 20,000. But then the next time we run it, we get some weird number, 13,051, completely wrong. Right, so what the heck is going on here? Okay, so to understand that, we have to look at the assembly language for this counter loop, so that we need to look at the assembly language for this counter loop in the thread routine. So we'll break it up into 3 chunks. The first chunk is sort of getting ready for the loop. We'll call that the head, and we'll denote it as h of I for thread I. And then we'll isolate on these 3 instructions that are directly related to incrementing count. Okay, so you see the first instruction it loads the value in global variable count into register RDX. So we'll denote that as L of I. Next, it increments RDX. We'll denote that U of I for update. So it updates RDX. And then it stores the updated value of RDX into count. Okay, so into the location associated with the global variable count. And and then the rest of this loop is getting ready to do the next iteration. It's not directly related to incrementing count, so we'll just sort of group this all together and refer to it as T of I for tail. Okay. Now, let's look at how these two threads might be executed. And remember, in general, we can't assume that there's any specific interleaving. So any interleaving of these two threads is possible, no matter how remote it might seem. So let's look at one example. Let's say we're executing on a single core, so we're only going to do one instruction at a time. And in this column, we'll show which thread is executing, so either thread 1 or thread 2. And then we'll denote which instruction in that thread is executing, either H, L, U, S, or T. And then this column shows the value of RDX for thread number 1. And this column shows the value of RDX for thread number 2. Right? And since the kernel keeps separate copies of all the general purpose registers, for each thread, these can be different. Okay, and then this last column shows the value of count in memory. So let's start executing. So initially, count is equal to 0. And thread 1 gets, the kernel schedules thread 1, so it executes H1. That has no impact on count. Then thread 1 loads the value of count into its copy of RDX, updates it, so now RDX is equal to 1, and then stores that value in RDX back to count. So now count is equal to 1. Now at this point, the kernel decides to schedule thread 2. So thread 2 begins executing. And when it begins executing, value of count is 1. So it executes H of I. Then it loads count into thread 2's copy of RDX. So now RDX equals 1. It updates it. Now it's equal to 2. And then stores that value back to count. The kernel then decides, and then it finishes executing the tail instruction. And let's say we're just doing one iteration of this. And then at this point, the kernel decides to schedule thread 1 since thread 2 is finished. So thread 1 executes the remaining statement that it has to execute. And at this point, both threads have finished. And count is equal to 2, which is the value we would expect. Okay, so this is okay. And notice how, so this is an interleaving that works. Okay, we get the correct value. And notice how I've grouped the 3 instructions that are actually involved in updating count together. And we'll call those 3 instructions the critical section, and I've color-coded them so you can easily keep track of them. All right, let's look at another interleaving, which is feasible, right? But in this case, it results in the wrong value. Okay, so here we start with thread 1 again. It loads the value of count into its copy of RDX, updates it, but then before it can store it, the kernel decides to schedule thread 2. So thread 2 begins executing. It loads count into its copy of RDX2. You notice count is still 0, right? It's 1 in the value of in thread 1 in the RDX, the copy of RDX in thread 1, but it hasn't been updated in memory. So when thread 2 loads its value of count, now its copy in RDX is 0. Now at this point, the kernel reschedules thread 1 to execute. So thread 1 does its store of its copy of RDX into count. and then finishes executing the tail instruction. The kernel reschedules thread 2, which picks up where it left off. It updates its copy of count. So now RDX goes from 0 to 1. And then it stores that value into count. So all we've done is we've overwritten, count had a value 1, and we've overwritten it with a value of 1. So when we finish execution of these two threads, count has the wrong value. Okay, and the general thing to notice is, you see how these critical sections have been interleaved, right? In this case, the critical section for thread 1 executed before the critical section for thread 2. Okay, but in this case, the two critical sections interleaved. Okay. So let's see another example of that. So here you can see that these are interleaved. So you probably suggest there might be a problem. Yes?
Specify that I is volatile without this problem?
So, excuse me?
Specify that I was volatile without saving it to a register?
Well, no. Okay, so the question is, would I or count? Count.
I just used I, but
If we, okay. It is defined as volatile, didn't I? Yeah, so that's why, I mean, there's actually, and the compiler could have compiled this code in different ways, right? There is actually an increment instruction that will increment a variable in memory. So we could have done, the compiler could have generated this 3 instruction sequence as one instruction, and then we wouldn't have this problem. But the problem is that it's loading into a register, then incrementing, and then saving. So that the problem comes about because we can, this thread can be interrupted before it finishes this 3-step sequence, this load, modify, store sequence. Yes?
the volatile keyword doesn't actually prevent things from being stored in the register. It just means every time you store it, the first one in the memory.
It would put, yeah, so that's right, yeah, I guess I wasn't clear. It prevents it from being stored permanently in a register, right? So it may have to be loaded into a register, but then it'll be written back. Okay. Whereas the compiler would have the option, like we've seen it with local variables, right? The compiler just, it never allocates stack space. It just keeps that local variable in a register all the time. Okay, so this the volatile attribute prevents the compiler from doing that. Okay, so let's look at another example. So here thread 1 starts. It loads count into RDX. Then thread 2 starts, and it loads count, which is still 0, into RDX2, updates it, and then stores it. So now count equal to 1. When thread 1 resumes, it updates its value of count in RDX and stores that back to count. And so again, we have the same problem. Okay, so the problem here is that we're interleaving these critical sections. And you can understand why this is bad with a nice sort of graphical technique called a progress graph. So in a progress graph, if we have, for n threads, it's an n-dimensional Cartesian grid that characterizes the execution state space of a concurrent threaded program. So in this case, here we have 2 threads, so it's a 2D coordinate system. So each axis represents the progress, the execution progress of some thread. So the x-axis here is thread 1, and the y-axis corresponds to thread 2. And then each one of these edges corresponds to the execution of an instruction. Okay, so we start out in an initial state, and then the first thing we execute is H1. So that's represented by this arc here. So this this position, this point right here represents the state where we've executed we finished executing H1 in thread 1, but we haven't yet executed any instructions in thread 2. Okay, so in general, each one of these points represents sort of the current progress of the program or the execution state. So for example, this state right here represents the state where thread 1 has completed L1 and thread 2 has completed S2. And now, the execution of a program is modeled as a transition from one state to the other. And there's some, so from this, and there's constraints on how, on how these states can advance. So from this state, L1, S2, yeah, obviously time can't go backwards, right? So we can't go backwards like in this direction to the left, and we can't go down. Okay, so we can only go to the right and up. And since we're assuming that each instruction executes, there's only one instruction executing at a time, we can't go diagonally. That would be 2 instructions. Right, so from L1, S2, the next execution state is either here, if thread 1 executes, or here, if thread 2 executes. Okay, so you can put all these together to form a trajectory which characterizes one execution of the program. Right? And any feasible set of transitions from one state to the next corresponds to a feasible trajectory. Right? So for example, H1, L1, U1, H2, L2, S1, T1, U2, U2, S2, and T2, that's a feasible trajectory. And it's it represents one possible execution, or sort of one set of interleavings for this program. Now these three instructions, L, U, and S, that manipulate count, form what we call a critical section with respect to count. And the idea is that instructions inside these critical sections, with respect to the same global variable, shouldn't be interleaved. Okay. So we can capture this geometrically by taking the intersection of these critical sections to form what we call an unsafe region. So in this, an unsafe region is the points within an unsafe region are those points in an execution where the critical sections are interleaved. Okay, so for this particular example, there's 4 points within the unsafe region. And if a trajectory ever touches one of those points, then we've interleaved critical section and we're going to get the wrong answer. Okay. So the idea is to try to stay out of these unsafe regions. And if we do, we say that trajectory is safe. So here's an example of a trajectory that's safe. Now this is okay, right? This point right here is not in the unsafe region because we've only executed H1 here. Okay, remember a point corresponds to the instruction that we've completed that instruction. So then, so here we're skirting the unsafe region, but it's still okay. So this is a safe trajectory. We'll get the right answer for this one. However, this trajectory is unsafe because it enters the unsafe region at this point here. And even though it quickly exits, there's an interleaving there that creates a potential for the incorrect answer. Okay, so the question is, how do we guarantee a safe trajectory? And this is what we call synchronization. So somehow we want to sort of configure the kernel so that it'll never schedule an unsafe trajectory. So how do we do that? So somehow we have to synchronize the execution of those threads. And another way to think of this is that we need to guarantee mutually exclusive access to the critical sections. Right? So once the kernel begins, once a thread starts executing the first instruction in its critical section, we don't want it to be interrupted by another thread that has a similar critical section. Okay, we don't want it to be interrupted. We don't want one critical section with respect to a certain global variable to be interrupted by another thread that has, that's currently within that same critical section. Okay. Sorry. Yes, question?
Yeah, going back on that problem, how frequently does that bug occur? It seems unlikely to me that the correct answer of 20,000 will ever be returned.
Okay, so the question is, how likely is it that you get a correct trajectory? And it happens, right? You can run it, sometimes you do. It just depends. Usually it's wrong, sometimes it's right. And it just depends on how the kernel scheduled it, and you can't assume any particular scheduling. Right? So if you say, if you want to claim that you would never get the right answer, then you're assuming that the kernel's always going to schedule the unsafe trajectory, but you can't assume that. And in fact, it doesn't. Sometimes you just get lucky. And it turns out you have to call this function with a pretty big number in order to trip it up. It makes sense, right? Usually what the kernel does is that we can only reschedule a thread, swap it out and schedule another thread in when there's some exception, okay, so that passes control back to the kernel. So these exceptions are in two forms, either making system calls, so that'll trap into the kernel, so that's a form of exception, or the timer interrupt goes off, which transfers control back to the kernel. So the timer is going off on intervals of like milliseconds. Right? So if we're just doing one iteration in each thread, when a thread gets executed, the chances are very low that the timer is going to go off while that thread's executing, its little loop. But we're not making any system calls, right? So there's nothing that'll, we're not passing control back into the kernel ourselves. So the only way the kernel is going to get access is if the timer interrupt goes off. So if we're doing a very small number of iterations, the probability that, say here's the timer interval, it's going off at intervals like this, here, this, the probability, that thread would have to have been scheduled right before a timer interrupt would go off for it to interrupt that one or two iterations. So it turns out we have to call this function with with n iters being fairly large, so that the probability of the timer interrupt going off during that loop gets increasingly large. Does that make sense? So the classic solution from this comes from the early 1960s. One of the most famous computer scientists, a Dutchman named Edgar Dijkstra. And he came up with the classical first solution to this problem, which is what we're going to look at. Okay? And it's still the first. It's fundamental and very general purpose. And there's been many iterations and variations on this idea. But semaphores were the first and classic solution, which we'll look at. Okay, so a semaphore is a non-negative global integer that's used as a synchronization variable by two kernel functions called P and V, or two system calls called P and V. These P and V correspond to the Dutch words, but we just call them P and V, right? You just have to learn what they do. So each of these takes as an argument a semaphore. And the P operation has the following semantics. If S is non-zero, then decrement it by 1 and return immediately. Okay. And this test, that it's non-zero, and the decrement occur atomically. Okay, so they'll never be interrupted. Right. However, if S is 0, then suspend this thread until S becomes non-zero, and that thread then is restarted by a V operation. Okay, so if the semaphore is 0, P just blocks. It just gets suspended until it gets restarted by a V operation. And then after it restarts, the P operation now can decrement S by 1 and return control to the caller. Okay, the V operation just increments S by 1. And this increment, unlike that count plus plus that we just looked at, that increment occurs atomically. Okay, so it can never be interrupted. And then after it increments S, it checks to see if there's any threads that are blocked in a P operation. So you can think of, the kernel just keeps a queue of threads that are blocked in a P operation. And the V operation, after it increments S, it checks that queue for any threads that were blocked, because when they did the P operation, the semaphore was 0. And then it restarts exactly one of those threads in some indeterminate order, okay, in some order that you can't assume. It just picks one using some selection algorithm. And then it unblocks the suspended process, okay, which then completes its P operation by decrementing S. Okay, this seems like really simple, but it can be kind of hard to get your head around the first time you see it. So are there any questions about P and V? Okay, so the key idea of these definitions of P and V is that it imposes an invariant on the semaphores called the semaphore invariant, which is that for a semaphore S being operated on by P and V operations, S is always greater than or equal to 0. Okay. Now that doesn't seem very exciting, but it turns out this is a very useful property that will allow us to enforce mutual exclusion on these critical sections. So the P and V operations are provided by P threads in the form of 3 functions. There's a sem init functions, which initializes the semaphore to some value. Okay, so semaphores can be initialized to any value greater than or equal to 0. Sem wait is the P operation, and sem post is the V operation. Okay, and because I'm old school, I provide wrapper functions for those in your CSAPP.h file called P and V. Okay, it's also more compact too. Okay, so recall our buggy program called badcount.c, which was giving us the wrong answers for count. So how do we use semaphores to fix this program? So the basic idea is to create a semaphore which is initialized to 1. And so by definition, we'll call any semaphore which is initialized to 1 that's used to provide mutual exclusion, we'll call that a mutex. Okay, and this goes back to the early Dijkstra papers. So we'll associate a unique mutex initialized to 1 for each shared variable in our program. Okay, so in this case, count, we have count, so we have one shared variable that we're concerned about. So we'll create one mutex that we'll call mutex. And then you surround the critical section with respect to count with a p, you call p, then you execute the critical section, and then you call v. Now there's some terminology we'll use when we talk about semaphores. So a binary semaphore is a semaphore whose value is always 0 or 1, and then a mutex is a binary semaphore that's being used for mutual exclusion. The p operation is called locking the mutex. We'll refer to a v as sometimes unlocking or releasing the mutex. And if a process is holding a mutex, then that means it's been locked but not released. So mutexes and binary semaphores are always initialized to 1. A counting semaphore, and the mutex is used for mutual exclusion, but you can also use semaphores to count sort of events in the system. And oftentimes for those, counting semaphores have sort of non values that are greater than 1. Okay. So for mutual exclusion, to fix our program, we create a new program called goodcount.c. And here we initialize a mutex, or we create a mutex and initialize it to 1. And then we surround the critical section, which is the 3 assembly language instructions embodied that implement this count plus plus instruction. We surround it with a p followed by a v. And if we do that, we always get the right answer. Okay. But you know, p and v are system calls, so there's overhead associated with these. So they're not free. In fact, they're orders of magnitude. This program runs orders of magnitude slower than the incorrect buggy version. All right, so why do these mutexes work? So here we've got a progress graph now where we've decorated our program with p and v operations. So we put the p before the critical section. We execute the critical section, and then we call v. And now if you were to look, you remember p and v, p increments the semaphore, p decrements the semaphore, v increments the semaphore. So if you were just to look at the value of that semaphore for every point in the execution state space, you'd get these values. So here we initialized the semaphore at the origin. We initialized it to 1. So the value of our semaphore at the origin is 1. And let's say we just move along. So we're just executing thread 1. So after H1, the semaphore is 1. We do the P. The semaphore is 1, so P just decrements it and proceeds. So now the semaphore value becomes 0. And it remains 0 until we execute the V. And when we finished executing the V, the semaphore now is 1 again. Okay, so if we go through a similar reasoning, if we look at the trajectory to get to any point in this state space, so let's say this point right here. So to get there, we could execute thread 1 up to this point, finish the L1, and then execute H2, and then do at this point, the semaphore is 0, and then P decrements the semaphore, so now it's -1. But that's impossible. That can't happen because P blocks. Remember, if the semaphore is 0, P blocks. It doesn't decrement it. Okay, so the semantics of the P operation prohibits this transition. It prohibits this transition to the state where the semaphore is 0 to a state where it would be -1. And so it creates what we call a forbidden region. So these points in the state space where the semaphore would have a value of -1 are infeasible. They can never be reached by the definition of P and V. Okay, so this forms a forbidden region around the unsafe region, and in doing so provides mutually exclusive access to the critical sections in each thread. Okay, so this is the fundamental reason why P's and V's can be used to provide mutually exclusive access. So any questions on this? I explained it so clearly that there's no questions. All right, good. Well, you get to leave early then. Work on your Malik lab. So, all right. So we'll see you Monday. We're going to look at some advanced topics. This was like our first introduction to synchronization. On Tuesday, we'll look at more advanced topics in synchronization and ways that you can use semaphores to provide other interesting kinds of synchronization for your programs.